Deep within the constellation, Leo, 120 light-years from Earth, something extraordinary was found, something that would shake the foundations of everything we thought we knew about our place in the cosmos. A faint signal buried in infrared light, a signature hidden within wavelengths invisible to human eyes. On an ordinary morning at Cambridge University, a scientist named Niku Madusan stared at a screen and saw the impossible. The atmosphere of a distant planet had revealed a trace of a molecule that should not be there. A molecule that, on Earth, is produced only by living things. Dimethyl sulfide. A name unfamiliar to most, but to scientists, it speaks volumes. It is not just a chemical, it is a biological fingerprint. And it had arrived in data captured by humanity's most powerful eye in space, the James Webb Space Telescope. The light carrying this signature had traveled across the abyss of interstellar space for over a century, weaving through dust, radiation, and time itself. When it finally reached the golden mirrors of Webb, it whispered a story older than our nations, deeper than our oceans. A story that begins not with certainty, but with awe. For in that moment, one possibility became very real. We are not alone. Orbiting a red dwarf star in the constellation Leo, the planet known as K218b, lies approximately 120 light-years from Earth. From a distance, it may seem like just another point of light in the endless night sky, but this world is anything but ordinary. K218b resides in what astronomers call the habitable zone, a narrow band around its star where temperatures are just right for liquid water to exist. Unlike most exoplanets we have discovered, this one offers more than potential. It offers conditions that may be even more stable, more life-friendly than our own blue world. K218b is classified as a super-Earth, a category of planets larger than Earth but smaller than Neptune. Its mass is more than 8 times that of our planet, and its radius is over twice as wide. This makes gravity on K218b almost 3 times stronger than what we experience on Earth. A person weighing 150 pounds here would feel the crushing pull of over 400 pounds there. And yet, this immense gravity is not a burden, it is a blessing. It helps the planet hold on to a thick atmosphere, one that shields its surface and creates conditions where life could thrive. The atmosphere of K218b is unlike anything found in our solar system. Instead of being dominated by nitrogen or oxygen, it is composed primarily of hydrogen, one of the lightest and most ancient elements in the universe. This hydrogen envelope acts like a planetary blanket, trapping heat and redistributing energy across the entire globe. It maintains temperatures that are surprisingly stable, even on the night side of the planet, which never sees sunlight. On Earth, hydrogen is a trace gas. On K218b, it defines the very nature of the world, an alien sky, thick and warm, rich with the possibility of life. Across the vast surface of K218b, the temperature hovers at a steady 120 degrees Fahrenheit. It is the warmth of a summer afternoon, the heat of a healing bath, gentle, stable, and persistent. This temperature is no accident. It is the result of an elegant balance between the energy from its red dwarf star and the thick hydrogen atmosphere that wraps the planet like a thermal cocoon. Unlike Earth, where temperatures fluctuate wildly from poles to equator, K218b offers consistency, a world where warmth is not fleeting, but a permanent feature of the landscape. On Earth, a greenhouse effect can spiral out of control, as it has on Venus, turning worlds into ovens. But on K218b, the greenhouse effect works in reverse. The hydrogen atmosphere does not trap heat excessively, it regulates it. Heat from the star is absorbed and then redistributed evenly across the planet, preventing one side from freezing and the other from burning. Even the night side, locked in perpetual darkness, remains warm enough to sustain liquid water. This reversed effect is not just rare, it is extraordinary. It creates one of the most thermally balanced environments ever observed beyond our solar system. Beneath the thick clouds of hydrogen lies a vast ocean unlike anything on Earth. It is not made of pure water alone, but of water mixed with hydrogen under immense pressure. This hydrogen-infused ocean does not freeze easily, nor does it boil away. It remains stable across a wide range of conditions, forming a liquid world that may stretch hundreds of miles deep. In this dark, warm abyss, life could flourish without interruption for eons. The ocean itself may serve as a chemical cradle, where molecules collide and combine in ways that foster complexity and spark biology beyond our imagination. While Earth dances delicately between ice ages and heat waves, between extinction and survival, K218b offers something far more rare: stability. Its thick atmosphere, massive gravity, and the steady burn of its red dwarf sun create a planetary system designed for endurance. Unlike our own star, which will swell and consume Earth in a few billion years, K218's red dwarf will shine for trillions. K218b is not merely habitable, it is enduring. It is a world where evolution has time to unfold slowly, where ecosystems could thrive undisturbed, and where the story of life might be written across a canvas far more patient than our own. It began with light, faint, ancient, and stretched thin by the long passage of time. As the planet K218b passed in front of its host star, a tiny sliver of starlight filtered through its atmosphere. That light, barely touched by alien clouds, carried within it the secrets of the planet's chemical soul. Buried inside that spectrum, invisible to human eyes, were clues. And on a quiet December morning, Niku Madusan, a planetary scientist at Cambridge University, stared at a transmission spectrum that would change history. What he saw was not noise, not error, but signal. A whisper from a world 120 light-years away. This signal came in the form of absorption lines, tiny dips in brightness where molecules in the atmosphere of K218b had absorbed specific wavelengths of infrared light. Each molecule leaves a unique fingerprint, and astronomers are trained to read them like a script. At first, they detected water vapor, then methane, then carbon dioxide. Each one exciting, each one promising. But what came next silenced the room. The spectrum revealed the presence of a molecule that should not exist on a lifeless world. A molecule that, on Earth, is produced exclusively by biology. Dimethyl sulfide. Dimethyl sulfide, or DMS, is not created by volcanoes. It is not made by lightning, by comets, or by chemistry alone. On Earth, it is produced by life, by marine plankton, bacteria, algae, and certain plants. It plays a role in cloud formation and climate regulation, but it begins with living cells. And now it had been found elsewhere. Not as a trace, not as a maybe, but in measurable, repeatable quantities. The James Webb Space Telescope had picked up its presence not once, but across multiple observations. The odds of it being a false signal were less than 3 in 1,000. In science, that is close to certainty. The detection of dimethyl sulfide was a shock, not because it was exotic, but because it was familiar. It is a signature of life as we know it. Not an ambiguous hint, but a direct echo of Earth's biology, now imprinted on the atmosphere of a distant world. No other known process can account for it. Not photochemistry, not rock interaction, not thermal reaction in deep planetary cores. Its presence means one thing: something alive is breathing on K218b. Something real, present, and powerful enough to leave its mark in the starlight. The presence of dimethyl sulfide alone would have been astonishing. But what truly surprised scientists was its strength. The signal was not faint or tentative. It was bold. So strong, in fact, that it could be measured from 120 light-years away through the thick veil of an alien atmosphere. On Earth, such levels of dimethyl sulfide are only produced by vast, ocean-spanning ecosystems, billions upon billions of microorganisms exhaling together. This was not the breath of a single cell. It was the collective exhalation of an entire biosphere. A planet, it seemed, was alive. This was not the chemical whisper of a world just beginning to flirt with biology. It was the confident voice of a world where life had already taken hold. The amount of dimethyl sulfide detected suggests that biological processes on K218b are not isolated, primitive, or struggling. They are active, thriving, and widespread. It may not be a world of forests and animals, but it is certainly a world where life has matured beyond the microscopic. A biosphere capable of reshaping the atmosphere, of balancing complex chemical cycles, of leaving fingerprints in starlight. Dimethyl sulfide may be the headline, but it is far from the only story. Alongside it, the James Webb Space Telescope detected water vapor, methane, and carbon dioxide. Each of these molecules is familiar, even comforting. On Earth, they form the very foundation of our biosphere. Water supports all life. Methane is produced by microbes in wetlands and animals alike. Carbon dioxide fuels photosynthesis, and breathes through every forest. Together, these molecules form the metabolic heartbeat of a living planet, and now they have been found on K218b. The significance lies not only in their presence, but in their combination. These gases, coexisting in measurable amounts, should not remain stable in a dead atmosphere. Methane and oxygen, for example, destroy each other over time. Yet here, in the skies of K218b, methane and carbon dioxide persist together. This chemical imbalance, this disequilibrium, is the mark of life constantly renewing the system, a dynamic, ongoing process that mirrors Earth's own balance between life and chemistry. K218b is not just showing signs of habitability, it is demonstrating activity, intention, and perhaps resilience. Sometimes, the absence of a signal speaks louder than its presence. On K218b, scientists noticed something strange, not in what they found, but in what they did not. Ammonia, a molecule that should be abundant in a hydrogen-rich atmosphere, especially on a lifeless planet. On gas giants and dead worlds, ammonia tends to accumulate. It does not break down easily without active chemistry. But on K218b, it was missing. Not in small amounts, but almost completely absent. The most likely explanation? Something is removing it, not machines, not weather, but biology, alive, responsive, and at planetary scale. Nature loves balance. Left alone, chemical systems settle into equilibrium. Gases react, stabilize, and drift toward quiet uniformity. But life is disruption. Life breaks balance and remakes it constantly. On Earth, our atmosphere holds both oxygen and methane, gases that should cancel each other out. They remain only because living organisms keep producing them. The same phenomenon appears on K218b. Methane, carbon dioxide, and dimethyl sulfide coexist in ratios that defy chemistry alone. This imbalance is not noise, it is signal. A living world breathes unevenly, chaotically, beautifully, and that chaos is detectable. K218b is not a frozen rock locked in chemical stasis. It is a dynamic system, one where molecules appear, vanish, and appear again. The planet is not just holding on to heat and water, it is recycling them. It is processing carbon. It is breaking down methane. It is sculpting its own skies. Every signature detected by the James Webb Space Telescope suggests a biosphere not just present, but active. It is a planet that does not merely host life, it participates in it. From cloud to ocean, from surface to stratosphere, the planet itself is alive. Dimethyl sulfide is not a simple molecule. On Earth, its production requires complex enzymes and coordinated cellular pathways. Its creation is a biological act, one that implies structure, function, and evolution. If life on K218b is producing DMS, then it must possess at least some of the same biochemical ingenuity found in Earth's marine life. The presence of methane alongside it strengthens this possibility. These are not random molecules drifting in from comets. They are products of metabolism, chemical whispers of organisms performing work, extracting energy, shaping cycles, and surviving. What kind of life could survive in a hydrogen-rich ocean under triple Earth's gravity with no oxygen to breathe? We do not know, but the presence of biologically linked molecules suggests that nature has found a way. Life on K218b may have followed a different path, based on hydrogen, not oxygen, on pressure, not sunlight. But the logic of evolution still applies. If enzymes exist, they evolved. If cycles are stable, they were selected. This is not just a living planet, it is an evolving one, and it challenges everything we thought we knew about what life needs to begin. "1 million miles from Earth, suspended in silence at a gravitational balance point known as Lagrange 2, a golden mirror stares into the darkness. This is the James Webb Space Telescope, the most powerful space observatory ever built by human hands. Its purpose is nothing less than extraordinary: to see further, to see deeper, and to see what no telescope has seen before. With a primary mirror over 20 feet wide, made of 18 gold-coated hexagons, Webb is a precision instrument that stretches the limits of physics. It does not orbit Earth, it orbits knowledge itself, facing the cold depths of space, waiting for the faintest signals from distant worlds. Unlike telescopes that use visible light, Webb is designed to see in infrared. It sees heat, not color. This is crucial because the signatures of life, like water vapor, methane, and organic molecules, shine brightest in the infrared spectrum. These signals are often drowned out in visible wavelengths, but in the infrared, they whisper clearly. Webb is built for that whisper. Its instruments are kept colder than the surface of Pluto, shielded from sunlight by a 5-layer sun shield the size of a tennis court. This extreme cold allows Webb to detect the warmth of planets, stars, and galaxies too faint for any other telescope to find. The method is elegant. When a planet passes in front of its star, a small portion of starlight filters through the planet's atmosphere before reaching Webb's mirrors. That starlight carries with it the molecular fingerprints of the gases it passed through. Different molecules absorb specific wavelengths of light. Water vapor, for example, leaves one pattern. Methane, another. Carbon dioxide, still another. Webb captures these absorption lines with extraordinary sensitivity, building what scientists call a transmission spectrum, a cosmic barcode that reveals the chemical makeup of a distant world. It is how we now read the air of planets we will never touch. These transmission spectra are not photographs, they are data, pure and complex. But within these lines lies the story of a planet's climate, chemistry, and possibly biology. It is how we discovered dimethyl sulfide on K218b. Not by flying there, not by sending probes, but by interpreting the tiniest dip in a line of starlight that had crossed interstellar space for over a century. James Webb turns photons into patterns, and patterns into meaning. It is a machine that transforms the invisible into knowledge, converting silence into signal. And in doing so, it allows us to hear the breath of alien worlds. Imagine trying to spot a firefly next to a stadium floodlight while standing 1,000 miles away. That is the challenge of seeing an exoplanet beside its host star. The star outshines the planet by billions of times. But Webb has a secret weapon, the coronagraph. It is a device designed to block out the blinding light of a star while allowing the faint glow of nearby planets to shine through. Like creating an artificial eclipse, the coronagraph masks the center of the star's image and reveals the hidden world orbiting nearby. Without this, the light of the planet would be lost in glare forever. But blocking the light is not enough. Starlight bends, scatters, and sneaks around corners. It creates speckles, false images that mimic planets. To overcome this, Webb combines the coronagraph with advanced wavefront correction and image processing powered by artificial intelligence. Every mirror segment must be aligned to within billionths of a meter, every vibration dampened. Webb must hold its position in space so steadily that it is like aiming a laser at a coin on the moon without ever drifting. This astonishing precision allows it to distinguish real planets from optical illusions and to find chemical fingerprints buried in the glow. The James Webb Space Telescope can detect the heat of a bumblebee on the surface of the moon. It can measure the temperature of a planet 120 light-years away, with an error margin of only a few degrees. It can identify a single molecule among trillions of photons. To do this, it must analyze light with an accuracy of 1 part in 10 million. This is not just an instrument of astronomy, it is an extension of our senses, built with gold, mathematics, and silence. Webb does not just observe, it listens to the universe breathe, one photon at a time. Every time the James Webb Space Telescope observes a planet, it returns not a photograph, but a flood of raw data. Millions of measurements, recorded in narrow bands of infrared light, each hiding a secret. To decode this avalanche, scientists do not rely on human eyes alone. They turn to artificial intelligence. Machine learning algorithms sift through the noise, separate signal from artifact, and spot patterns no human could detect. Dimethyl sulfide, for instance, would have been buried without AI to recognize its spectral fingerprint. Webb may be built of metal and mirrors, but it thinks with silicon and speed. Hubble showed us beauty. It captured glowing nebulae, galaxies in collision, and the silent grandeur of the cosmos. But it was bound by the visible spectrum, light that our eyes can see. James Webb goes further. It pierces dust, shadows, and time itself. Where Hubble sees surface, Webb sees structure. Where Hubble sees brightness, Webb reads chemistry. It has given us our first real breath from another planet. Not a guess, not a dream, but data. Webb does not replace Hubble, it extends it. And in doing so, it stretches the reach of human perception far beyond what we once believed was possible. For as long as we have looked up at the stars, we have asked one question more often than any other. Are we alone? From ancient myths to the philosophies of Plato, from Galileo's telescope to Carl Sagan's golden records, this question has never left us. It is the heartbeat of human wonder. For centuries, we have searched for an answer in silence. But today, silence gives way to signal. The discovery on K218b may not yet be confirmation, but it is the closest we have ever come. For the first time, the question is not just poetic, it is scientific, and the universe is whispering back. We have long imagined other worlds, places where life might exist, given the right temperature, the right chemistry, the right atmosphere. But all of it has been theory, until now. On K218b, we have captured more than speculation. We have detected chemical fingerprints, methane, carbon dioxide, water vapor, and a molecule called dimethyl sulfide. On Earth, DMS is created only by life. This is not proof, but it is a threshold, a crossing. We are no longer guessing, we are measuring. The breath of an alien world has touched our instruments, and it has changed the way we ask the question. The shock is not just in what we found, it is in how different it is from us. K218b is nothing like Earth. Its gravity is more than twice as strong. Its oceans may be hydrogen-rich. Its skies are thick with haze, not blue with oxygen. Yet in this alien chemistry, we see signs of biology. This forces us to rethink everything. For centuries, we assumed life must look like ours, oxygen-breathing, carbon-based, born in sunlight. But maybe life is not rare. Maybe our definition is too narrow. K218b reminds us that the universe is not limited by human imagination. Life finds a way, even in forms we have never dreamed. Dimethyl sulfide, hiding in spectral lines, is more than a molecule. It is a challenge. It tells us that life may thrive without oxygen, without Earth-like cycles. It tells us that biology is not a local accident. It might be a cosmic pattern. This is a biological revolution, unfolding not in laboratories, but in the light of distant worlds. What we once called exotic, we must now call expected. Life, it seems, does not need to look like us to exist. And that realization shifts the center of everything we know. There was a time when humanity believed the Earth was the center of everything. Then came Copernicus, and the heavens moved. Now, the discovery of a possible biosignature on K218b moves the center again. Not just astronomically, but biologically. If life exists elsewhere, then Earth is no longer a unique cradle of existence. It becomes one example among many, perhaps billions. This realization is not a loss, it is a liberation. It reminds us that life is not a miracle confined to one blue dot, but a principle written into the very fabric of the cosmos. For centuries, we have placed ourselves at the top of a silent hierarchy, assuming that intelligence, civilization, and even biology itself were rare achievements. But K218b whispers a different story. Perhaps we are not the first. Perhaps we are not the only. And perhaps intelligence is not the peak, but one thread in a wider, richer biological tapestry. The idea that we may not be special is not a threat. It is a revolution of humility. It shifts our identity from rulers of a solitary Earth to participants in a vast and ongoing experiment called the universe. The discovery on K218b is not just a scientific milestone, it is a beginning. Astrobiology, once considered fringe, now stands at the center of a new era of exploration. No longer are we simply asking where life might exist. Now we are developing the tools to detect it, characterize it, and perhaps even communicate with it. Space telescopes, planetary missions, machine learning, and atmospheric chemistry are converging into a single question: what is life beyond Earth? K218b may be the first test case, but it will not be the last. The universe is large, and we have only just begun listening. We are witnessing the birth of a new kind of science, a biology that does not begin in a petri dish, but in the light of stars. It is a science that must embrace the unknown, where the rules of life are not written by evolution on Earth, but by conditions we have never seen. In this cosmic biology, oceans may be made of methane, skies thick with ammonia, and yet life might still thrive. K218b shows us that biology is no longer a local affair. It is a universal question, and the answers may be more diverse and surprising than anything our textbooks have prepared us for. K218b is far away, so far that no ship will reach it in 100 lifetimes. But distance does not diminish its meaning. This planet, with its signals hidden in light, has reached across space to touch something in us. It has invited us to see life not as an earthbound miracle, but as a possibility written across the stars. It does not speak, and yet it calls. It does not know us, and yet it reflects us. In its silence, K218b has become a mirror, not of who we are, but of who we might become. This is not just about K218b. It is about the way we see ourselves. Once we believed we were alone. Now we must ask if we are early, or simply one among many. The universe has opened a door not to certainty, but to possibility. Through that door, we glimpse a cosmos where life is not an exception, but a rhythm, where the breath of one distant planet becomes the first note in a universal song. And perhaps, if we listen carefully, we will learn the melody was never ours alone. K218b may be the loudest signal we have found so far, but it is far from alone. Across the galaxy, we have discovered thousands of exoplanets, many of them orbiting within the so-called habitable zone, where liquid water might exist. Worlds like TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, rocky planets circling a cool red star, are prime candidates. Others, like LHS 1140b, appear to have thick atmospheres and stable orbits. Even Proxima Centauri b, our nearest stellar neighbor, shows hints that it could host liquid water. The list is growing. Each name on it is a possible story waiting to be told. Every planet we add to this list expands our imagination. It tells us that the conditions for life might be far more common than once believed. We no longer assume that Earth-like worlds are rare. Instead, we begin to suspect that planets with the right ingredients, warmth, liquid, and chemistry, are the rule, not the exception. And the more telescopes we launch, the more refined this census becomes. Soon, with upcoming missions like the Nancy Grace Roman Space Telescope and the European Plato Observatory, we may identify hundreds more worlds that resemble K218b, or perhaps ones even more Earth-like. But what exactly are we looking for? Life does not announce itself in pictures. It leaves behind a scent, a whisper, a chemical fingerprint. Scientists call these biosignatures, molecules that, under certain conditions, can only be produced by life. One of the strongest is oxygen, especially when found alongside methane. These two gases should destroy each other, yet if both are present, something must be producing them. Other candidates include ozone, which protects against ultraviolet light, and nitrous oxide, a byproduct of biology. Together, these signals form a growing dictionary of what life might look like on other worlds. Thanks to the James Webb Space Telescope, we can now read these signatures directly from the light of distant stars. As a planet passes in front of its star, a small portion of starlight filters through its atmosphere. Molecules in that atmosphere absorb specific wavelengths, creating shadows in the spectrum, lines we can read like barcodes. It is in this spectral language that we first spotted dimethyl sulfide on K218b, and it is through this same technique that we are beginning to scan dozens of other planets for similar signs. We are no longer guessing, we are interpreting. No single molecule proves the existence of life. Even dimethyl sulfide, powerful as it is, must be considered in context. The strength of biosignatures comes from combinations, chemical imbalances that should not occur naturally. For instance, large amounts of both water vapor and methane, with no known volcanic source, may hint at microbial activity. A planet that continually replenishes unstable gases could be breathing. These patterns, these subtle inconsistencies, are not noise. They are the echoes of biology. The universe may not shout its secrets, but it leaves clues. And for the first time, we are learning how to listen. Sometimes, the search for alien life does not require traveling to distant stars. Some of the most intriguing candidates lie within our own solar system. Titan, the largest moon of Saturn, has lakes and rivers, not of water, but of liquid methane and ethane. It rains hydrocarbons and breathes an atmosphere thicker than Earth's. Enceladus, smaller but active, shoots plumes of vapor from cracks in its icy crust. These geysers contain water, hydrogen, and organic molecules. Europa, a moon of Jupiter, hides a subsurface ocean beneath a frozen shell. Together, these worlds defy expectations and invite serious scientific curiosity. What makes these moons compelling is not just the presence of water, but the combination of energy and chemistry. On Enceladus, The Cassini spacecraft flew through a geyser and found molecular hydrogen, a potential energy source for microbial life. On Europa, the gravitational pull from Jupiter may heat the ocean from below, creating hydrothermal vents like those that support ecosystems deep beneath Earth's seas. And Titan, despite its alien chemistry, may offer a parallel path to life, one based not on water, but on methane. Each of these worlds could host a biosphere unlike anything we know. On Earth, life has a reputation for resilience. Microorganisms have been found living inside volcanic vents, beneath miles of ice, and in acidic lakes where no fish could survive. There are bacteria that eat rocks, thrive in radiation, and endure near boiling temperatures. These organisms, called extremophiles, show us that life is not fragile. It is, in fact, relentless. If life can exist in the most hostile corners of Earth, then similar forms might survive under the icy shells of Europa or within the methane lakes of Titan. What we once thought of as limits are now seen as possibilities. For decades, scientists searched for Earth-like planets, worlds with the right distance from their stars, with temperatures that allow for liquid water. But the lessons from our own solar system suggest that this view may be too narrow. Life may not require sunshine, oxygen, or even liquid water. It may thrive in cold, dark oceans heated from below, or in chemical soups beneath alien skies. Habitability is no longer just about Earth's twin. It is about energy, chemistry, and time. The universe, it seems, is much more inventive than our imaginations have been. The more we explore, the clearer it becomes. Life does not need to resemble us. It does not need blue skies or green plants. It might not breathe oxygen or depend on sunlight. The universe may be filled with forms of biology that are silent, hidden, and completely unfamiliar. This realization does not make life rarer. It makes it more likely. And it means that every icy moon, every methane lake, every distant exoplanet is no longer just rock and gas. It is a question waiting for an answer that only exploration can give. In the vast silence of space, a few moments stand out like whispers from the unknown. In the year 1977, a radio telescope in Ohio recorded a burst of energy so distinct, so unexpected, it was marked with a single word: wow. It lasted only 72 seconds and was never heard again. Since then, other signals, brief, powerful, often unexplained, have sparked both fascination and skepticism. Fast radio bursts, mysterious pulses from deep space, arrive without warning and vanish just as quickly. Are they natural? Or could some carry meaning? The cosmos offers no answers, only more questions. Across the globe, powerful observatories are now scanning the skies not just for stars, but for patterns, repetitions, symmetry, anomalies in time and energy. Projects like Breakthrough Listen have begun to monitor millions of stars, searching for signals that might suggest intelligence rather than randomness. The logic is simple. Nature creates beauty, but rarely precision. A repeating transmission, a narrow band pulse, a signal that returns in intervals. Such things would stand apart from natural noise. We have not yet found them. But the search itself is a mirror of human curiosity, a willingness to believe we might not be alone. Some scientists now suggest that life and intelligence might be not accidents, but inevitable outcomes. That the universe, governed by laws that allow complexity, is wired to produce observers, beings that can reflect, question, and seek meaning. This idea stretches beyond biology into philosophy. If stars forge the elements for life, and gravity gathers planets in stable orbits, perhaps the cosmos is not indifferent. Perhaps it is participatory. We are not separate from the universe. We are one of its ways of knowing itself. In that light, intelligence is not a fluke. It is part of the structure. Imagine the universe not as a cold mechanism, but as something more organic, a process that evolves, adapts, and generates novelty. Like a living cell, it holds structure and flow, feedback and emergence. Galaxies are not static. They swirl, merge, and seed new stars. On countless worlds, chemistry stirs and cycles, some perhaps moving toward consciousness. What if the universe behaves like a living system on the largest scale? Not alive in the way we define biology, but alive in principle, dynamic, generative, and creative. This is not mere poetry. It is a lens through which new science is beginning to look. If life is common and intelligence arises more than once, then the universe may already be filled with minds asking the same questions we do. And if consciousness is not bound to Earth, then the cosmos is not a lonely expanse, but a rising chorus of awareness. Perhaps stars give birth to planets, and planets give birth to life, and life gives birth to thought, not as isolated events, but as part of a cosmic arc. The universe, through us, and perhaps through others, is beginning to perceive itself. And in that awareness, something astonishing emerges. The universe is not only matter, it is meaning. For most of human history, we believed we were the center of everything. The stars circled us, the heavens sang of divine order, and Earth was a cradle made for our presence. Then came the quiet revolutions, Copernicus, Darwin, Hubble, each one humbling us, shrinking our cosmic importance. But what hurt most was not our size. It was the silence, the deafening quiet of a universe vast beyond comprehension, yet seemingly empty. In that silence, we began to ask a deeper question, not whether we were central, but whether we were alone. And that question has haunted us ever since. Loneliness on Earth is bearable. There is always another voice, another heartbeat nearby. But in the cosmos, loneliness becomes something else entirely, a metaphysical ache, a feeling that perhaps all of human history, every triumph and tragedy, every painting, every poem, has unfolded in a solitary corner of a vast and indifferent theater. We send probes, we listen to radio waves, we scan the skies for familiar chemistry, and for decades, the answer has been silence, until now. A distant world named K218b has changed the equation, not by screaming, but by whispering something profoundly unfamiliar. Life may not be ours alone. The discovery of dimethyl sulfide on K218b was not just a chemical surprise, it was a philosophical rupture. For the first time, we encountered a potential sign of biology on a planet far beyond our reach. This was not science fiction. It was spectral data, measured, analyzed, confirmed. And with it came a quiet realization. We may no longer be the only living world. This changes everything. If life exists elsewhere, even in microbial form, the era of human exclusivity has ended. The universe is not sterile. It is alive. Or at least, it has begun to reveal its living parts. K218b does not know our stories, our languages, or our telescopes. And yet, it breathes. Perhaps not with lungs, but with a planetary metabolism, an atmosphere that cycles, a surface that responds, clouds that hint at motion and chemistry. It exists entirely independent of our awareness, and that is what makes it so important. For centuries, we believed life required Earth. But now, here is a world that may contain life without ever knowing us. It reminds us that life is not a miracle confined to one blue dot. It may be a thread that runs through the fabric of the universe itself. The discovery of another living world, even if distant and unreachable, shifts our place in the cosmos. We are no longer a miracle, we are a member. No longer the exception, we are part of a pattern. The stars above are not cold watchers of our existence. They are hosts of other possible stories. And in that knowledge, something dissolves. The boundary between us and the universe. We are not simply in the cosmos, we are of it. The atoms in our blood were forged in ancient stars. The curiosity in our minds echoes the structure of the galaxies themselves. To belong is not merely to exist. It is to be part of something greater, to be woven into a larger whole. When we understand that life may emerge wherever conditions allow, then Earth is not the exception. It is one example among many. The cosmos is not a vast emptiness, but a fertile sea of potential. And we are not drifting alone in the dark. We are riding a wave that began long before us, and that may continue far beyond us. This is not the end of our story. It is the beginning of a new one where we are no longer isolated observers, but conscious participants in a living universe. What happens to a civilization when it realizes it is not alone? For centuries, our myths, religions, and stories have placed humanity at the center. The heavens were created for us. The stars, silent and eternal, served as backdrops for our dramas. But now, that narrative trembles. If life exists beyond Earth, then every poem, every song, every painting suddenly belongs to a broader conversation. We are no longer performing on a stage set for one. We are part of an orchestra, many instruments, many melodies. Culture does not collapse, it expands. The question of who we are gains a deeper dimension. The discovery of life elsewhere also becomes a mirror. It reflects how we treat the unknown, how we approach difference, how we define us and them. Will we react with fear, as we often have in history when confronted by the unfamiliar? Or will we respond with humility and awe, recognizing that we are one expression among many? The arrival of this realization forces us to revisit ancient questions. What is intelligence? What is morality? What is worth preserving? The presence of others challenges not just our science, but our ethics, our governance, and our vision of the future. What if we are not the only ones watching the stars? What if, somewhere out there, another form of life has already passed this threshold, has already asked the same questions, faced the same silence, and reached out across the void? Would we recognize their signal? Would we understand their language, their intention, their fears? More importantly, would we be ready? Not technologically, but emotionally, psychologically, spiritually. The first contact may not arrive as a spaceship in the sky, but as a philosophical event, a shift in our inner landscape, and how we respond will define the legacy of our species. There are moments in history that redefine what it means to be human. The discovery of fire, the first footprints on the moon, the decoding of our genetic code. These events change not just what we know, but how we think, how we dream. The confirmation of life beyond Earth will be such a moment. It will alter our place in the universe, not physically, but existentially. It will tell us that consciousness is not confined to one planet. That thought, wonder, and longing may echo across many worlds. And in doing so, it will awaken a new kind of responsibility, one not just to Earth, but to the cosmos itself. We have spent lifetimes fearing the silence of the void. But what if the silence was never empty? What if it was simply waiting for us to learn how to listen? K218b may be the first whisper of an unfolding chorus, a sign that life does not dwell in isolation, but in a vast web of connection. To move beyond fear is to open ourselves to relationship, across time, across species, across worlds. This is not a science fiction dream. It is the beginning of a cosmic dialogue, one that invites us to step forward not as rulers, not as invaders, but as companions in the great unfolding of existence. If the universe is alive with potential, then our future is not limited to Earth. We are no longer bound by the narrow horizon of our atmosphere. We have the chance to build a new kind of destiny, one where intelligence is not a solitary flame, but a constellation of lights scattered across time and space. The first signal from a distant world is not just a discovery, it is an invitation to grow beyond what we have been, to imagine, to reach, and to become part of something far greater than ourselves. The future is no longer earthbound, it is cosmic. The moment humanity ceases to be alone in the universe will not arrive with a thunderclap. It will come in the quiet hum of a computer, in the whisper of data filtered through silence. A scientist will look up from a screen and realize that what they are seeing is real. Life, confirmed not in a dream, not in fiction, but in spectra, in molecules, in the breath of a distant world. That realization will not end our story. It will begin a new one. For the first time, the loneliness that has shadowed our species since we first looked up at the stars will dissolve into something larger, something infinitely more connected. K218b is not just a planet, it is a mirror held up to our own existence. In its skies of hydrogen, its stable heat, its planetary breath of dimethyl sulfide, it tells us a story we were always meant to hear. That life is not an accident. That life does not need to mimic Earth to flourish. And that we, on our pale blue dot, are not the only chemistry to awaken to thought. The discoveries made by the James Webb Space Telescope have torn open the veil of cosmic isolation and shown us a galaxy that may be more alive than we ever dared to imagine. Not empty space, but living ecosystems, each with its own history, its own potential, its own voice in the cosmic choir. From here, the path forward changes. Every telescope we build, every mission we launch, every signal we send into the void now carries new weight. Not just curiosity, but responsibility. We must become guardians of knowledge, of exploration, of life itself beyond Earth. We may never visit K218b, but we can learn from it. It has already changed us. And as our technology sharpens and our imaginations expand, we move forward with eyes wider, questions deeper, and hopes lifted by the realization that the universe is not only knowable, it is alive. The age of cosmic loneliness is ending. The future, vast and full of life, begins now. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.